Hello, welcome back to System Dynamics class. This is Practicum Module 4 entitled as Solving Differential Equation Using Transfer Function Method. Let's start with what is transfer function. Consider a dynamic system which is a car that is vibrating in vertical direction due to the excitation of the engine. This system is modeled as a mass that is suspended by a spring with constant of K and a damper with constant of C. The excitation of the engine, the excitation that is produced by the engine is represented by Ft, which is force as a function of time. Meanwhile, the response of the system is Xt, the displacement of the mass with respect as a function of time. In order to describe the dynamic characteristic, we will correlate the response and the excitation. To obtain that relationship, we draw the free body diagram of the system, that is mass. There is an excitation, which is force, Ft. Due to the spring, there will be a force upward, Kx. Due to the damper, there will be force of Cx dot. And then, as this mass is accelerated downward, then there will be inertial force as much as mx double dot upward. So this force is in the opposite direction of x double dot. Then, based on this free body diagram, we derive an equation based on sigma fx is equal to 0. Okay, since we use the Alembert method, which involves inertial force, the equation is sigma fx equal to 0. And then it will be mx double dot plus cx dot plus kx minus ft is equal to 0. Okay. Then we arrange this differential equation as something like this. Okay, so this differential equation actually represents the dynamic characteristic or the dynamic behavior of the system. However, this equation is complicated since we have x and its derivative, which is x dot and x double dot. So it still involves derivation. In order to remove the differential, we apply Laplace transform to the equation, so we will have another equation which is something like this. We can see here that there is no differential anymore involved in the equation. Based on this equation, we can arrange this equation, xs, where xs is the Laplace transform of the xt, of the vibration, and fs is the Laplace transform of the excitation. Okay, so it is equal to 1 divided by ms squared plus cs plus k. This function is called as transfer function. So transfer function is another way we represent the dynamic characteristic of the system. In this case, the dynamic characteristic correlate the response and the excitation by a rational function, which is response divided by excitation. Okay, so we name this as GS. So GS is the transfer function. By definition, this is response divided by the excitation. Okay, so this is the transfer function. So in a simple way, we can say that transfer function is an equation representing the dynamic characteristic of the system by correlating the output and the input using rational function in S domain. Okay, now the next one, what is Laplace transform? Yeah. Okay, Laplace transform, yeah. By definition, the Laplace transform of a function ft is a semi-infinite integral of ft multiplied by e minus st with respect to time. Okay, so where s is a complex number, yeah, sigma plus j omega, yeah, where j is square root of minus 1. This is an imaginary number. Okay, so this is definition. And then as we perform the integral to the function, then we will get, as a result, we will get another function uh, as a function of s. So in this case, the fs is the Laplace transform of the ft. Yeah. Okay. And then for dx dt, yeah, for dx dt, this is the first derivative of x with respect to time. If we take the Laplace transform of dx dt, then we will have s multiplied by big X as a function of s. So xs in this case, yeah, xs is the Laplace transform of x as a function of time. Yeah. Okay. Minus initial condition x0. Yeah. So this is the first property of Laplace transform you have to remember. Yeah. And then the second one is the Laplace transform of the second derivative of x with respect to time. It will be s squared xs, where xs is the Laplace transform of xt, minus s initial x, initial value of x, minus dx dt. Yeah, I think this one dx dt when t is equal to 0. Yeah. Okay, so if all initial conditions are 0, we can cancel this out. Cancel this out, cancel this out. So all we have is just sxs for the first derivative of x, and then we will have s squared xs for dx squared dt squared. Okay, so as a result, if we take the Laplace transform of our differential equation we have derived from the free body diagram, so it will be something like this. Yeah, the x double dot will be s squared xs because we neglect the initial condition. Initial conditions are zeros, and then the x dot will be s multiplied by xs, and xt will be xs. Last one, the ft will be fs. Okay, so for students who haven't got explanation regarding Laplace transform in the class, simply you can use Euler style, yeah, in for derivative, uh, d square for second derivative, dx t for the first derivative of x, yeah, and then all you need to do is just to replace the d by s. So d square become s square, d become s, yeah, xt will be xs, yeah, all xt will be xs, and the ft will be fs. Okay, so this is the shortcut for you, for students who haven't got explanation regarding Laplace transform in the class. Okay, now let's learn how to find the Laplace transform using MATLAB. Yeah, uh, you can type help Laplace, yeah, in order to obtain an explanation regarding Laplace transform using MATLAB. Okay, let me jump to the example. Have a look here. Yeah, so initially we need to declare all variables that will be involved in our equation. Yeah, for example, a is as a constant, s is the Laplace domain, t is time, w for another constant, x is the function, And then this one is function ft is a function of time. Okay, so the Laplace t power 5, yeah, it will be 120 divided by s power 6. Yeah, so mathematically we can write this as the Laplace transform if the xt is equal to t power 5, then the Laplace transform of xt, which is Laplace transform of t power 5, yeah, which is by definition this is the semi-infinite integral of e minus st t power 5 the xt dt. Yeah, okay, so if you perform this integral, then you will get 120 divided by s6, something like this. Okay, yeah, so similar to that, you can obtain several functions. Yeah, you can obtain Laplace transform of several functions. And then let me show you this. Yeah, Laplace diff ft. Yeah, remember that in my previous slide. Yeah, it means that the Laplace transform of diff is differential, so it is dft by dt, yeah, is equal to s multiplied by, yeah, s multiplied by the Laplace transform of ft, the Laplace transform of ft, yeah, uh, from t to s, yeah, minus f0. Yeah, okay, so it is actually I can simplify this as fs. Yeah, so fs is the Laplace transform of ft minus f0. Okay, so exactly the same as what I have done on the previous slide. Yeah, okay, this is how we obtain Laplace transform of any function, yeah, by utilizing MATLAB. And then let me show you how to obtain the Laplace transform of our equation. Yeah, have a look. This one is m diff diff double diff. So it is actually mx double dot, yeah, plus uh, c multiplied by diff x, which means cx dot, plus kx. Yeah, and then the Laplace means that I'm performing Laplace transform of these terms. Yeah, and then it results in k Laplace xt, so it is equal, which means that it is, yeah, this one is let me write here, this one is k xs. Yeah, okay, remember that this one is Laplace transform of xt. Yeah, it transforms the function from domain of t to domain of s. Okay, so it will be xs. And then this one is sx0. Yeah, we assume that initial condition is 0. Yeah, uh, and then this one is s square. Yeah, minus s square. Yeah, actually I have made this result pretty big. I make this become prettier, yeah, by applying pretty ends. So it will be k xs, right? And then this one is minus m, yeah. This one is 0, yeah. Inside the bracket there is minus and minus become plus, s square Laplace transform of xt, so it will be xs, right? Plus what is this, dx dt when t is equal to 0. Again we assume that this one is equal to 0, yeah, which means that the dxt by dt when t is equal to 0 is equal to 0, the initial condition. And then the last one, we have c, yeah, This is equal to 0, minus and minus become plus, so it will be CS XS. Yeah. Okay, so the Laplace transform of this one, yeah, these terms is KXS plus MS square XS plus CS XS. Yeah. On the other hand, the Laplace transform of Ft will be Laplace of Ft from T to S, which means that it is equal to Fs, right? Yeah, okay, so this is how we find the Laplace transform of any function using MATLAB. Okay, okay, let's go to the exercise number 1. Yeah, we are going to review on how to find the differential equation using integration method. In module 3, actually you have learned uh, how to find this differential equation using integration method. Yeah. Okay, from case number 1, this is x double dot plus 3x dot plus 2x is equal to 1t. Yeah, basically this one is ft. Yeah, ft, where ft is equal to 1t. 1t is a unit step. 1t is equal to 0. Yeah, for t less than 0, and this one is 1 when t is greater or equal than greater than 0 or equal to 0. Yeah, so in this one is something like this. Yeah, stepping at t equal to 0. This is time, this is the ft, yeah, the function. This is 0, this is 1. So the function is stepping from 0 to 1 when t is equal to 0. Yeah, stepping here. This is called as unit step function. Unit step function. Yeah. Okay. Meanwhile, RT, yeah, is a ramp function. Yeah, RT is ramp function. It is some. It appears something like this. Okay. So this one is T and this one is FT. Yeah, and this is RT. Yeah, the slope is equal to 1. Yeah. Okay, actually RT, yeah, RT can be written as T multiplied by 1T. Yeah. So this is, if we have a function of RT is equal to T, then it will be something like this, right? But as we multiply this, multiply this by a unit step, then we will have a ramp function, yeah, which is equal to 0. So mathematically we can express RT, yeah, RT as, yeah, it's equal to 0 if t less than 0. It is equal to t if t equal to or greater than 0, right? Okay, sine function, I think you have got familiar with this. Yeah, and this one is the initial condition, yeah, associated with the differential equation. Yeah. Okay, let's have a review. Yeah. Okay, first please open your Simulink by typing Simulink on your command window, and then click on blank model. Yeah, this is your blank model, and then click on the library. Yeah, then you will have two windows, something like this. Okay, so it will be your program. Yeah, you are going to write your program here, and then this one is the library. All you need, all component you need is available here. Yeah. Okay, firstly, yeah, as usual, as you have done in module 3, please take a summation block, something like this. Yeah, two integrals, 1 over s, this is integrator, two integrators. Uh, this one integrates the x double dot, yeah, x double dot becomes x dot, and then this one transform the x dot become x, and then this is the scope. Yeah. Okay, and then please do double click on the sum. Yeah, and then the list of signs must be plus, minus, minus, which means that we want to have something like this. Yeah, this is the output. Yeah, this is the output. It means that we want to have plus, minus, and minus. Yeah, we need three ports or three terminals, yeah, that will be connected to another component. Okay, so this is the complete circuit, the complete program. Yeah, please drag again here. Yeah, then also put another gain here. Yeah, then connect the gain with the others. Yeah. Okay, and then this one is the step function. You can obtain this one from sources here. Yeah, and then you have to find step function. Yeah, this is function step function. Yeah, okay, let's see. What we do here is actually please do double click on this one. Yeah, the gain must be 3 and then this one must be 2. Okay, if you remember our practicum in module 3, yeah, it is x dot, x double dot, it is x dot, and then it will be x. Yeah, then the x dot, yeah, will be multiplied by 3 and then it will be 3x dot. Yeah, meanwhile this one, after you do double click on the gain, this gain, it becomes 2, something like that. Okay, and then it will be 2x. Okay, so the differential equation, is represented, mainly represented by this sum. Yeah, where uh, x double dot, yeah, is equal to minus 3x dot. Yeah, the minus comes from this sign. Yeah, this sign is negative, and then we have another negative there. Yeah, minus uh, 2x. Yeah, and lastly plus, this is the ft. Yeah, plus ft. Okay, so if you rearrange this equation, you can write this one as x double dot plus 3x dot plus 2x, that is equal to ft. Yeah. Okay, so that's why we always express the equation in form of x double dot equal to. Yeah, because uh, this x double dot is the summation of ft minus 2x and minus 3x dot. Yeah. Okay, and then do double click on the step function. You need to customize this by changing the stepping time. By default, the stepping time is at t equal to 1 second. This is ft. Yeah. So the default function provided by MATLAB is something like this, which means that it is stepping at t equal to 1 second. Yeah, meanwhile, our function, our simulation requires a unit step that is stepping when t is equal to 0, which means that this is what we want. Yeah, this is what we want, the red one. Yeah, so you need to customize the step time at 0, not at 1. Yeah, this is the initial value. Yeah, the initial value. This is the initial value. Yeah, and then the final value is set as 1. This is the final value. Yeah. Okay, then once you complete your program, all adjustment has been done. Yeah, what you need to do is to run. Yeah, by clicking this symbol and then do double click on the scope, then you will get the result. So it is, yeah, it represents the xt, yeah, versus time. Yeah, have a look. Yeah, this one is the axis of time. Yeah, this is t. Yeah, and this one is the vertical axis is the xt. Yeah, because our scope is connected to x. Yeah, not to x dot, neither to x double dot. Yeah. Okay, this is how we obtain the solution. Yeah, the solution of the differential equation using integration method. Why we call this? The reason is because we involve these two integration blocks. Yeah, 1 over s is integral and this one is integral. So this is called as integral or integration method. We have uh, done several exercises in module 3, yeah, using this method. Now let's make a comparison by performing another simulation for the same differential equation. Remember that the differential equation is plus 3x dot plus 2x is equal to ft, yeah, where ft is a unit step function, something like this. Yeah, and then what I do here is I'm clicking continuous. Yeah, I'm opening the continuous menu. Inside this menu there is transfer function, so please drag the transfer function to your program. Yeah, and then do double click on the transfer function to customize. Yeah, have a look. Yeah, this one, as you do double click on the transfer function, then this there will be a pop-up menu. Yeah, allowing us to edit the parameter of the transfer function. Yeah, uh, the variables or the parameter you have to adjust, yeah, are numerator. Yeah, and this one is the denominator 132. Okay, so 1 means that one which means that the numerator is 1. Yeah, 1 t true represents the coefficient, which means that this is 1 s square plus 3s plus 2. Yeah, okay, so 1 3 and 2, yeah, are the coefficient of polynomial. Yeah, okay, remember that our equation is x double dot plus 3x dot plus x is equal to ft. Yeah, so the Laplace transform of this equation will be s square xs plus 3s xs plus xs, yeah, equal to fs. Yeah, if you arrange the transfer function, which is gs, yeah, by definition this is the response xs divided by the excitation of or the input, it is equal to 1 divided by s square plus 3s plus 1 uh, plus plus 2, yeah, plus 2x, sorry, this one is 2x, so it is plus 2, plus 2. Okay, you can see that the coefficients are 1, 3, and 2. Then you deliver this to this matrix array. Yeah, don't forget to hit or click apply, then OK. Yeah, okay. Once you click OK, then the transfer function will be updated. Yeah, so you can see that actually this one is the xs divided by fs. Yeah, then all you need to do is just you need to connect this input to the ft, yeah, to the unit step function, this one. Yeah, you connect this and then also click this, yeah, to there, to the scope. Oh yeah, this one is a multiplexer. Yeah, so in commonly used block there is mux, which is multiplexer, then drag it there. It makes your scope behave as an oscilloscope with two inputs. Similar to an oscilloscope with two inputs. Then you connect this to there. Yeah, this one. Okay, so you connect the output of the transfer function to the second channel of the scope. Meanwhile, this output must be connected to the first channel of the scope. Then you hit run, run button, and then you do double click on the scope. Then you will get two plots. You cannot see the difference because this one is exactly the same as this one. Okay, so the transfer function method is much simpler than integral method. Since you just need to involve one block only, which is transfer function. But remember that this method is applicable only for applicable only applicable only for x0 is equal to x dot 0 is equal to 0. So all is 0. All initial condition is 0. Let me show you that if the initial condition is not 0, for example, I'm doing double click on the integrator here, and then the initial condition is 0.2. I'm changing the initial condition. Then I perform the same simulation by click run button here, and then do double click on the scope. Then this is what you will get. So this is from transfer function, and the yellow one comes from the integral method. You can see that the initial condition is equal to 0.2, which means that the x0, this is x, right? So since we have set this one, do double click on this one, and then we set the initial condition as 0.2, then the x0 will be 0.2. You can see that the result, the xt, is completely different, not identical. So be careful. Please note that transfer function method can replace the integral method if all initial conditions is 0. You cannot replace the integral method by the transfer function method if the initial conditions is non-zero. Okay, so please do exercise number 2. You need to perform in exercise number 2, solve problem number 1, number 3, and number 5. Why? Because number 1, number 3, and number 5, the initial conditions is 0. You cannot use transfer function for number 2, number 4, and number 6, because the initial conditions is not 0. Not 0. Okay, good luck. Please do this exercise. Now let's go to the next exercise. But before we do the exercise number 3, let me explain mechanical components, which are spring damper and mesh. For damper, as we apply a force of F, which is the command or the input, command or input, and this one is response or output, which means that we apply a certain of force, and then as a consequence we will have xt, right? Okay, by according to Hooke's law, Hooke's law, the force required by the spring in order to produce displacement of x is ft equal to a constant multiplied by xt. Okay, applying Laplace transform to this equation gives us fs equal to kxs. So the transfer function, which is the response or the output divided by input, is 1 over k. Yeah, this is a constant. Similar to that, for damper, yeah, naturally it requires or it produces force. Yeah, it requires a certain of force in order to move this moving point, yeah, by speed of with speed of x dot t. Okay, so the force is proportional to speed instead of xt. Yeah, uh, uh, unlike the spring, the force is proportional with x dot. Okay, and then I'm changing this Newtonian style of differential, yeah, by Euler style. Okay, this one is Euler notation. I mean, yeah, the notation of x dot is replaced by dx, and then I'm changing the d by s, and then I'm changing the xt by, I'm converting the xt into xs. Yeah, actually what I'm doing here is taking the Laplace transform of the function of the equation. Yeah, the ft become fs, and then it becomes csxs. Yeah, and the transfer function is 1 over cs. Okay, similar to the previous components, using second Newton's law, f is equal to ma. A is the acceleration or the second derivative of x with respect to time. Then the transfer function will be ms squared, right? Okay, so in exercise 3, please make your own transfer function. You can customize your function, and then you apply a certain of force. Yeah, for a spring, you have to apply this one first, and then you have to draw the xt. Yeah, xt against time, x against time. Yeah. Okay, and then for the next case, yeah, you replace the ft by ramp function. Yeah, you apply to here, and then you have to draw another xt. Yeah, in different piece of paper. Yeah. Also, you have to draw the xt for ft equal to sine function. Okay, you have to try these 3 cases for spring, these 3 cases for damper, and these 3 cases for base. Yeah, good luck. Yeah, exercise number 4 and number 5 actually combination of spring. Yeah, spring. This one is damper. Yeah, and no mess. Yeah, here this card is assumed to be messless. Yeah, no mess m equal to 0. Yeah, this one is actually the summation of this one. Yeah, have a look. This is ft spring. Yeah, yeah, plus this one. Yeah, so this is the combination of that. Yeah. Okay, so using this, this is ft. Yeah, this is ft, this is k, this is c. So ft is equal to, yeah, kx, k xt plus c xt. Yeah, then you perform the Laplace transform. Yeah, fs equal to k xs plus c, sorry, this one x dot. Yeah, and then it will be s xs, and then the transfer function gs equal to xs divided by fs equal to 1 over k plus cs. Yeah. Okay, so please do the similar simulation for these different inputs. Yeah. And this one is the transfer function. Then you, for this this is exercise 5. Yeah. Actually this is combination of mesh and spring. Yeah, so you have to do the similar process as I did beforehand. Yeah. Then you have to draw the xt versus time for these different cases. Okay, this is exercise 6. Exercise 6 is electrical circuit. Yeah. The question is draw IT versus T and V out versus T. Okay, so what I have here is actually an electrical circuit consists of capacitor with constant of C and a resistor with constant or resistance of R. Yeah. As we apply an input voltage V in here, there will be a response which is IT, yeah, current, electrical current, IT. It will be flowing here, flowing through the resistor downward, and then it goes back to there. Yeah. Actually, another response, there is another response which is output voltage. Yeah, this is output voltage. Okay, now let's derive the transfer function. Okay, based on uh, Kirchhoff voltage law, we can write that V in, yeah, as a function of time is equal to, yeah, let me do this. This is F, this is G, this is H. Yeah. This is G, this is H, this is H. Yeah, which is VFG as a function of time. Yeah, plus V uh, GH as a function of time. Okay, basically the V in itself is, yeah, is equal to V from F to H as a function of time. Yeah. Okay, so the Kirchhoff voltage law says that VFH is equal to VFG plus FGH. Yeah. Okay, now let's derive the equation V in T is equal to VFG is the voltage across the capacitor. The voltage is quantified by Q by C, yeah, the charge filling up the capacitor. Meanwhile, the C is the capacitance. Yeah. And then the voltage across the resistor is I multiplied by R, isn't it? Okay. Okay, so now let's write this one is Q is the integral IT dt, right, divided by C, plus I is a function of time multiplied by R. Then we take the Laplace transform of the equation. It will be V in S equal to, the integral gives us 1 over S is, yeah, and the constant is just the same, 1 over C, yeah, plus I S R. Okay, now let me collect the is. V in s equal to is, yeah, multiplied by 1 over sc plus, okay, it is plus r, so I'm writing r cs divided by sc, right? Okay, so v in s is equal to is multiplied by sc, this one 1 plus rcs, yeah. So the transfer function, yeah, g1s is equal to is the response divided by the excitation, yeah. It is equal to sc divided by 1 plus rcs. Okay, so this is the transfer function, yeah. Okay, now what I want to show you here is actually, yeah, we can do the simulation in MATLAB. Yeah, let me show you that. Here I'm declaring t started from 0 up to t up to 2, yeah, with step size of 0.001, which is 1 millisecond. Yeah, so it means that the t is equal to, it is matrix 0, 0.001 or 1 millisecond, 0.002 up to 2 second. Okay, so this is the matrix of time. This is the resistance. Yeah, the resistance is R is equal to 3 ohms. Yeah, and this one is the capacitance is 100. Yeah, power multiplied by E minus 3 is 10 minus 3 farad, which is equal to 100 millifarad. Yeah, or 0.1 farad. Yeah, and then we have done that g1, yeah, g1 is equal to cs divided by 1 plus csr. Yeah, so what I'm doing here, in order to simulate the transfer function, I'm declaring S first like this. Yeah. So S is TF. TF is transfer function of S. Yeah. Okay. Maybe you get confused with this symbol. Yeah. But this one is actually what I'm doing here is just declaring, yeah, declaring variable of S. Variable S. That's all. Yeah. And then the transfer function is declared as usual. Yeah, all you need to do is just to write the mathematical expression. Yeah, you translate this mathematical language into MATLAB language. Yeah. Okay, what is G2? Have a look. Yeah, G2 is uh yeah, sorry, I'm going back here because this one I is the response, right? On the other hand, we have another response. We can also consider this one as a response, another response of the system. Yeah, so I can correlate the v out as a function of time is just r multiplied by it, right? So by taking the Laplace transform of this equation, I will get that is divide the vs, yeah, v out s divided by is equal to r. Then I call this as g2s, the next transfer function. Yeah, so I can consider that I is an input and the v out is the output. Yeah. Okay, this is just the definition. This is just convention. Yeah, Actually, both are response. Yeah, both of I and V out are response of the system as a consequence of applying V in to the circuit, right? But in this case, yeah, I can also consider that this one is output. Meanwhile, this is the input. So I am declaring the second uh, transfer function correlating the V out and I. Then mathematically we can, based on Ohm's law, yeah, this is Ohm's law, we can prove that the transfer function is just a constant of R. Okay, so that's why I have G1 is R. Yeah. So the block diagram, yeah, we can represent this one as a block diagram. The system can be simplified as this one. Yeah. This is G1 S. Yeah. The input is V in S. The first output is IS. And then we have the next transfer function, which is G2S. G2S with input of IS, and the output is V out S. Okay, and then this one I can simplify this one become GS, that is equal to G1S multiplied by G2S G2S. Okay, so this is the simplification. V in S, and this one is V out S. Yeah. Okay. So that's why I define the G as the multiplication of G1 multiplied by 2. Okay. And then in figure 1, yeah, I simulate step G1. Okay. So step G1 means that this function, this command or this script, yeah, replaces this simulation. This is G1, this is step function, yeah, and this one is the response. Yeah, this is this one is V in T, and this one is I T against time. Yeah. Okay, meanwhile, this one is the step for G1, G2, and G. So what I'm doing here is actually I'm simulating two different transfer function, yeah, G1S multiplied by G2S. Yeah. What I'm doing here is I'm applying a step function here, yeah, V in, and this is V out. Yeah. To check whether G1, this is GS, yeah, to check if this one is equal to this one or not, yeah, I'm doing something like this, yeah, and then I'm observing the result using scope. Yeah. Okay, so actually you can also perform transfer function simulation not only using Simulink but also using MATLAB as I show you here. Yeah, it's up to you. You can use either MATLAB or Simulink to simulate the transfer function uh, to obtain the response. Yeah. Okay. The advantages of using Simulink is that the program is simple since it is graphical. Yeah. But uh, in MATLAB, yeah, there are some advantages uh, that you cannot get if you use Simulink. Yeah. For example, the first one is that You can customize by your own. You can customize the time of simulation easily. Yeah. For example, the step size is 0.001 or 1 millisecond. You can customize easily by changing this one, for example, 0.0001. It's up to you. Yeah. Also the the duration of the simulation can be chosen uh, at any period of time. In this case, I select 2 seconds. You can extend the simulation up to 200 seconds, by changing this one become 200. That's all. Yeah, so this is the first advantage. You can customize the duration of the simulation. And then the second advantage is that, yeah, you can easily customize the way in. Yeah, the way in, yeah, can be either step function, ramp function, sine function, or combination of any function. For example, you can also do this, create sine, let's say 2 pi t uh, plus, let's say, pi by 3, for example, plus, yeah, so this is v in t equal to plus cosine 3 pi t plus pi by 2, for example. So you can customize this easily. Yeah. Then the only row or the only command replacing the simulation is just this one. Okay, so it means that, yeah, you have the g, this is gs, yeah, the input is v in, yeah, t is the variable of the domain, and this one is the v out. Yeah. So this is how you obtain v out as a function of time. Yeah, what you do is executing the command of lsim. Lsim stands for linear simulation. Yeah, this is lsim. Lsim, which means that this is the linear simulation. Yeah. Then after you obtain the V out, of course, you just need to plot, yeah, the T V in, T V out. Then you can customize this one. Yeah. Okay, this is the result. Yeah, this is the input signal, and this one is the output signal. Yeah, in this case, which means that this is V in as a function of time, and this one is the V out as a function of time. Okay, so yeah, that's all my presentation for this practicum. Uh, please do the exercise, yeah, both using both of MATLAB, both of Simulink and MATLAB. Yeah, each of method, yeah, has its own advantage and disadvantage. Yeah, you must in the exam or in the post test, you must be able to select, yeah, which method that is the most efficient method. Yeah, if you still get confused which one is the best for the given problem, then you will get difficulty to solve the problems in the post test. Yeah, so please do all exercises in this module step by step, yeah, in order to understand the advantage or and the disadvantage for each method. Thank you very much. See you again in the next module.